My plan for today is to spend pretty much the whole time talking about assignment 1 and making sure everybody feels comfortable with it and can move forward. So if you're panicking about that, hopefully today will assuage all of your concerns and you'll walk out of here confident and able to do the assignment. Let's bring up a grid. Here is a grid. Let's suppose you are here, represented by a green dot, and you want to be here, represented by a red dot. I'm going for a very simple video game here, just so you can visualize this in your head. Which way should you go? Right, right? Maybe up, but right's really the one that has the biggest gap, and so it's pretty clear kind of east-northeast direction is really what you want to do to arrive at that red dot. So just about everybody knows the optimal path is something like bing, 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 maybe bing, 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 bing. Right? Okay. Now, of course, this depends how we weight it. It's conceivable that going up and going to the right have the exact same cost. Maybe it's possible that you can go diagonal in this game, in which case you should, because it saves you a step, right? Okay. Let's suppose you can't go diagonal. Then which path is better? Oops. This one or this one? The answer is they're exactly identical. This is called Manhattan distance because it's like Manhattan city blocks or taxi cab distance. If you drive a taxi cab, it really doesn't matter which block you turn on as long as you don't do something dumb like that. You're going to get the same cost at getting to the goal no matter which path you take. But that only happens in perfect grid worlds. And it's certainly conceivable that you have a world where instead of squares, there are hexagons. You ever played D&D with hexagons or something like that? There's all kinds of possibilities, so Manhattan distance is just a property of squares or grid worlds. Now, we as humans know the answer is go to the right. How does a computer know that? Yeah.
Compare the coordinates.
So if destination is greater than position, go to the right.
Yeah, and if it's less, then go to the left. And if it's equal, you're going to want to go up or down with property there, depending.
Yep, that will do it. What you have just invented is called greedy search. And the way greedy search works is it says, okay, here's my position, there's the position of the goal. Of all the steps I could take, this one, that one, or that one, or that one, which one gets me the closest to the goal? And it's going to be this one. And then at this point we say, okay, now of all the steps that I could take, there's there, and back to where I was, but it's not going to choose that one. Which one's closest to goal? Well, now it's this one. And if we keep on doing greedy search, guess what it's going to do? It's going to basically do that, which is the optimal search path for this problem. Yay, greedy search solves all of the world's problems, unless the problem is slightly more complex. Oops. So let's make the problem more complex by saying that navy blue represents an alligator pit. So if you fall on a blue square, the alligators eat you, you die. Okay? Now you as humans, in fact, let's do this so there's only one good answer. There, now there's only one good answer. What is the right answer? You want to go left, right? Everybody knows that's the answer, but how does a computer do the answer? And more specifically, suppose we implement greedy search, what will the computer do? Yay, I'm closer! Yay, I'm closer! Yay, I'm closer! I'm almost there! And then, badness happens, right? Or I guess it'll fall right in the pit if it can. It could be that the game is designed such that alligator pits are forbidden, or it could be that there's a big penalty for it. Whatever, the gist of the matter is, greedy search is dumb, right? Okay, so you as humans all know the right answer is to go left. Go left so you can get to the right. You know that because you're intelligent, and the right path is to do this. and then that, and then maybe you go down like this, and there you go. But how do you know it, and how could you code that up? How can the computer know it?
I guess I quickly just looked at all the possible ways to get there, and then I just chose the one that actually worked.
Yep. How do you code that up? Yeah.
Try breaking it down into components of the path you're going to take. Like you need to.
So hierarchically make subpaths. Yeah, that's a good solution, in fact. But doesn't segue nicely into what I want to say next. No, it's awesome. I'm just going to say, good idea, but hold the thought, because that's actually an optimization of what I'm about to teach next. So
check all futures and see which one.
Check all possible futures. Yeah, so, well, okay, yeah, that's the answer. So let's just do it. Here are the 4 possible futures from this present, right? And from each of those, there are 4 possible futures, and it just expands and expands and expands, right? Suppose blue is 1 time step in the future, and then we'll say orange is 2 time steps into the future. And then dark red is 3 time steps into the future. Did I mess one up?
The one your mouse is currently on, that should be brown.
Oh, you're right, it should.
Or
Poink,
red,
poink,
blue,
poink.
I don't know.
Okay, and then light green is all the places you can do it the next future, and so forth. Do you see what's happening here? Is there's a frontier of possible futures that we're exploring. Oops. And then that, I'm going to start reusing colors because I'm running out here. But as we expand along this frontier, we're exploring all possible future cases, and eventually the frontier will reach the goal. Will it not?
Yeah.
At the time when that frontier finally reaches the goal, then let's suppose we could go back in time and remember exactly which choices led there. This one went to there. This one led to there. That one led there, there, and like that. And okay, I cheated. You can't do that. But do you see that ultimately finds the right goal? It's just that it had to fork the universe at every single step in order to explore possible universes. We're now doing multiverse theory here. And if you could code that up, then you could find the path from where you are to where you want to go, right? My undo history won't go back any further, so now I got to painstakingly undo that all. That algorithm I have just described graphically for you is called breadth first search. That's what we're going to be using to solve assignment 1. But now I have to show you that this one, how to code it up, 2, how this problem even pertains to a puzzle, because that's totally different from a maze, isn't it? Or getting from here to there. Actually, I claim it's not totally different. It's kind of just about the same thing. But let's talk about why. Okay, so first of all, do you see that there is a frontier, and the frontier is expanding? And do you see that the frontier... let's put it this way. I'm going to do a continuous version now. In fact, I'll say start and goal with bad art. Basically, if we started here, the frontier is going to be expanding and expanding. Whoops, that wasn't a very circle-y circle. There's more circle-y. Until finally we reach the goal. And when we finally reach the goal, there's a path through the possible futures we explored that gets from the start state to the goal. I claim that by the time we reach the goal, we know the optimal path, not just a path. We know the best, shortest cost way to get from the start position to the goal. And I claim that's provably optimal. Do you agree with that? Why do you agree? Because I'm a professor and you're easily persuaded. You have faith in me, right? Yeah.
If there was a left optimal path, wouldn't it have
Yeah, that's a good answer. Do you see how in this particular case I'm drawing circles? And I'm using circles because, well, pretend they're nice, perfect circles instead of ovals. And I can do that because there are no walls. A circle covers meaning anywhere within the circle is the same distance to the edge, right? No, that's not true. From the center of a circle to the edge is the same distance no matter which way you go. There's no possible way we could find another route that started here and kind of went up here and circled back that would be shorter because we've explored everything within the circle, right? So by virtue of the fact we've explored everything in the circle, it means there's nothing that finds the goal any faster, because if there was, we would have already found it if it was faster. Can you see the reasoning there? Therefore, it follows that breadth first search is provably optimal. Now, is it still provably optimal if we add a alligator pit or walls or something that stops you from searching in all possible directions? It turns out it is still provably optimal, and the reason is if the wall stops you, well, it's going to stop searching there. But by the time it finds the goal, there can't be a better way to the goal, because if there was, it would have found it first. Let me give one more analogy to go with this. Anybody play a lot of video games? Take one of these semi-linear story type games where you're an adventurer and you go exploring. When you find an NPC and the NPC says, "The big treasure you're looking for is right through that door," what do? You go through every other door first because you want to make sure you have broken every pot and opened every treasure chest and explored every potential secret, because as soon as you go through that door, you're going to fight the big boss and you're going to beat the boss, and then the story's going to move on, and if you had missed a treasure, you won't have the chance to go back and do it, and you want, by the time you win the whole game, to have maximized your achievements, right? That is, if you're a hardcore gamer who's not just trying to win the game as quickly as possible. If you want to win the game as quickly as possible, greedy search. Go through the door, right? If you want to maximize your score, you want breadth first search, because you're essentially trying everything except for the goal. The reason breadth first search is provably optimal is precisely because it tries as hard as it can not to find the goal, with constraints of not being stupid. Okay, so let me show you an example of what I mean by you can be stupid. So we could start right here and go to there, and then go back to here, and then go to there, and then go back to here, and there, and back to here. And we could go back and forth in a loop for all of eternity and never find the goal. And if breadth first search was allowed to do that, it would, because it's trying to do everything it can except for find the goal. You see how that's total badness? Okay. We've implicitly made a rule here that you can't go to a state where you've been before. As long as you have that rule, you can't be in a state we've been before, because we've already found a faster way to get to those states. Then, breadth first search expands in a frontier, and that frontier will grow until it finds the goal. When it finally finds the goal, we know it's the best possible path, because if there was something else, we've already tried it. Okay? If I were to ask you on an exam, why is breadth first search optimal? You could explain what I've just said, right? Because if anything else were more optimal, it would have found it first, because it searches all possible paths instead of shooting for the goal. So in essence, greedy search and breadth first search are exactly the opposite. You see that? Greedy search goes straight for the goal. Breadth first search says, let's try everything that's not the goal. And then finally says, okay, we'll move one step further and try everything that's probably not the goal, and then move one step further and continue until, oh darn, we found the goal, the game's over, look, my score is optimal, I'll never need to play this game again, I'm done, move on to the next one. And this is what gamers do with their lives. Okay, that was kind of a slam on gamers. I like gamers, but it's true. All right, yes?
How memory intensive does it tend to be with breadth first?
Excellent question. How memory intensive is this thing? Well, I guess it depends how efficiently you've coded it up, for one, but what do we need to store for every one of these squares. In this case, at least XY position, right? Well, how big is the grid? In the worst case, the grid gets all full. In fact, actually in breadth first search, it won't get all full. Imagine a perfectly bounding circle around the start position that reaches the goal state. Or in the case of Manhattan squares like this, it'll be a perfect diamond because diamonds represent the frontier of equal cost. But as long as that's expanded from your start position to your goal, that's the maximal size of the state that you will have to explore. Yeah.
Want to get more maximal if you've got the alligator pit going further and further away from the...
Oh, so you're, yeah,
if the alligator pit,
let's
goes
suppose
1 kilometer up and
we've got a case of this. Now the frontier is going to have to grow until it reaches all the way around here and then can bleed back in to reach the goal. So yes, you're exactly right. What I just said a moment ago wasn't true. It's going to be the full size of the circle necessary to reach there plus the size necessary to reach from there to here. So I don't know if there's a simple way to draw it, but if you could imagine those two circles added together, that's kind of the maximum number of states that have to be stored internally in order to do breadth first search. Yes?